Hello. Having discussed about the space quantization as well as the electron spin involved, we will be discussing about the vector model of atom, which consists or which is on the basis of coupling of the orbital and spin angular momentum. Now, the total angular momentum of an atom results from the combination of the orbital and the spin angular momentum of its electrons. And since the angular momentum is a vector quantity, we can represent the total angular momentum by means of a vector, which is obtained by the addition of the vector addition, of course, of the orbital as well as the spin angular momentum vectors. And this leads to the vector model that we are about to discuss. Now, let us consider an atom whose total angular momentum is provided by a single electron, such as that of hydrogen, lithium, sodium. They are of the same kind. And the magnitude of the orbital angular momentum in that case, as we know it, is L. So this is the magnitude only. So L is equal to L times of L plus 1, that is the quantum number associated with it, h bar, and its z component is Lz is equal to ml times of h bar. Now, as you know, L is the orbital quantum number and ml is the magnetic quantum number, and ml can have values which are stretching right from minus L through 0 to plus L. S, the spin angular momentum, in that case the magnitude in that case is equal to S times of S plus 1 h bar, where S is obviously the spin quantum number and its Z component is given by ms h bar, which is the magnetic spin quantum number, which can only possess two values, that is plus and minus half, that is plus and minus of s being having the sole value, that is r. Half, s can have a value half. This is well, let me write this a bit different from the quantum number that we are using. Quantum number is smallest, and so this is the value of that smallest that we are having, uh, and this is the spin quantum number, and uh, the value associated with it is half, while the magnetic spin quantum number ms will possess plus or minus of s, that is plus or minus of half. So we have the total angular momentum in that case, that is j vector, is equal to the sum of the vector sum of L and S, that is the angular momentum, the orbital angular momentum and the spin angular momentum. According to the quantization conditions that we have studied so far, we can say that the J will have a magnitude which is given by J times of J plus 1 under root h bar. So J here is the inner quantum number, as we call it. J is the inner quantum number, and then similarly, if we consider the z component, then we have mj times of h bar, and that mj will have values stretching from minus j right up to right through 0 up to plus j, and they will be obviously the possible that will be the range of mj, and mj obviously here is the magnetic quantum number that is associated with the total angular momentum. And as far as the case of the angular momentum of the quantum numbers, the z components is concerned, we have jz to be equal to Lz, and because Sz can take a positive and negative values, so we have plus or minus of Sz, while the corresponding quantum numbers Mj is equal to Ml plus or minus of Ms, depending on what kind of value the Ms takes. Now, there's one more thing that tells us is that since we have Mj to be an integer, not Mj but Ml to be an integer, and we have Ms to take up either plus or minus half, so the quantity Mj from this previous relation that we discussed, that is Mj is equal to right there at the bottom, Mj is equal to Ml plus or minus of Ms. So Mj will take up those half integral values. Because of that spin quantum number, the magnetic spin quantum number, and that's why the maximum values of Mj will depend on whether the spin is positive or negative, and so we have J to be equal to L plus or minus of S. And as we have already discussed right now, that J will be a half integral. Now, since this total quantum number, the angular the orbital quantum number and the spin quantum number, they are all quantized. They can have only specific relative orientations. In case of a one electron atom, there are two relative orientations that are possible, which is because of the spin factor. That corresponds to, so we are considering the one electron atom, and in that case we'll have two relative orientations. And what will that be? Well, that corresponds to corresponding to J being equal to L plus S and J being equal to L minus S. And so in each case, that leads us to this angular momentum having a magnitude greater than the orbital angular momentum, that is the total angular momentum in that case, and here the total angular momentum has a value less than the orbital angular momentum. Two ways in which L and S can combine to form J can be given by considering the following figures that I am going to draw. So in each of these figures, you see in one of the cases L has a magnitude less than that of J, while in the second figure to the right you have L to have a greater magnitude than that of J. And that's because the resultant in each case that we have for the small l, that is the quantum number, magnetic quantum number, that being equal to 1 and the spin quantum number being equal to plus half in the first case, results in the total angular momentum to be total quantum number, the angular momentum quantum number, to be equal to 3 over 2. And then in the next case, because of the minus half, we have the value going down to be less than the value of L, that is L being equal to 1, you have the value of J to be equal to half only. Now the angular momentum of the atomic electron, that is in that case the L and S that we have, they interact magnetically, and that is what we call as the spin orbit interaction. They exert torques on each other, the torque that is applied, these internal torques, they do not change the magnitude of the vectors, but they cause them to precess uniformly around their resultant. The resultant that you see over here is J, that is the total quantum number. And these two, that is the orbital angular momentum as well as the spin angular momentum, they precess about the total angular momentum, and that is exactly what we call as the spin orbit interaction, how they interact with one another. Now if the atom is in free space, then no external torque will be acting on it. Then the total angular momentum is conserved in that case, both in magnitude and direction. And the angle between L and S, they also remain invariant, and therefore we will have a formula that is by which they can be related, the general formula of addition of vectors, which we will be writing down. But before that, I would like to provide you with one more figure related to what we are discussing, that is the spin orbit interaction. So in this figure, as you see, the angular momentum, the orbital angular momentum and the spin angular momentum, they precess about the total angular momentum. In the absence of an external field, they apply torque on one another, and as a result of that, they precess about the fixed total angular momentum. And you have the highly magnified view of the atom as well at the bottom, and these angular momenta, they behave and they interact with one another in what we see over here, in the manner that we see over here. So the vector equation that we can relate in this case is J squared is equal to L squared plus S squared. This is the case of resultant, and that resultant in this case is the total angular momentum. So J squared is equal to L squared plus S squared plus 2LS, and whatever is the angle between them, cosine of that, we write it with this notation, L comma S. So cosine of that angle between them. So what we can get is cosine of L comma S is equal to J squared minus L squared minus S squared over 2LS. And if we expand them in their quantum numbers, in terms of their quantum numbers, so we have J times of J plus 1, that was under root, but now it has opened up, and there's an H barred square multiplied to it, but we'll take care of it later. And in this case we have minus of L times of L plus 1, the under root has been squared, and similarly the case with S times of S plus 1. Well, the H barred squared, that is taken common from each of those terms, and what you find is in the denominator, because we are going to have two H barred terms as well, because there's an L times of L plus 1 H barred, and there's S times of S plus 1 H barred. The root over terms are kept, while the H bar squared is cancelled out with the numerator term. So we have cancelled out those H bar squared, and this is the vector model of one electron atom. It can be extended to many electron atoms as well. The vector model enables us to explain the phenomena which could not be understood by from the Bohr-Sommerfeld theory, such as the fine structure of spectral lines, the anomalous Zeeman effect, and the hyperfine structure as well. The conception of a spinning electron, which is a salient feature of the vector model, is responsible for the fine structure doubling of the alkali spectra lines. And now the energy of an electron in a given quantum state will be higher or lower depending on the orientation of the spin vector than its energy in the absence of the spin orbit interaction. This also means that each quantum state except for the S state, for which the angular momentum will be 0, that is splitted into two separate substates, which is a result of plus s and minus half values of s. This results in the splitting of every spectral line into two components, and that's the case of electron spin, which is so much of importance in this case. The numerical value of this splitting agrees with the experimental observations, and similarly spin orbit interaction together with relative correction explains the hydrogen's fine structure as well. Now, suppose we consider the existence of an external field, then what do we have? Like in this case, we observe that the L and S precess about J. In that case, J itself, in the presence of the external field, will be precessing about the external field, while L and S will continue to precess about the J vector, that is the total angular momentum. So this is the vector model that you are observing right now, where you have S and L to be precessing about J, while J precesses about the external field, and the discrete orientations of J relative to B, that is the external field, which involve slightly different energies, gives rise to the anomalous Zeeman effect that is to be discussed later, and it is in agreement with the experimental observations. Like electrons, the atomic nuclei also have smaller intrinsic spin, angular momentum, and also the magnetic moments as well. When these vectors are added to the atomic model that we have been studying right now, the experimentally observed hyperfine structure of spectral lines could be explained easily in that case. Now we move over to the segment where we discuss the spectroscopic terms and the notations that are related to them. Now, the quantized energy states, which are simply called the quantum states of an atomic electron, is described in terms of the quantum numbers. Quantum numbers, that is the principal quantum number, the orbital quantum number, the spin quantum number, and even the total or the inner quantum state or inner quantum number. The electrons having the orbital quantum number L is equal to supposedly 0, 1, 2, 3, and so on, they correspond to the names or the notations that are given to them is S, P, D, F. Now do not confuse this S with this S. It's not the one. That is the spin quantum number, and this S is simply for the subshell, that is S. The atomic states in the atom are specified by writing the corresponding principal quantum number along with these letters. Thus, for an electron with n is equal to 2 and L is equal to 0 will be denoted as 2s. 2 for the value of n and s for the corresponding value of L, that is equal to 0. And then again, for supposedly n is equal to 3 and L is equal to 1, we have 3p. We had already discussed this in one of my previous videos. If you probably look at the case of hydrogen atom that we had discussed prior to this, in that case, in that video, I have already discussed about this. Now, the energy levels of the electrons of an atom are called as the terms of the atom. Of electrons of an atom are called terms. Terms of the atom. The corresponding energies expressed as wave numbers are called term values. For a one electron atom, the energy levels corresponding to L is equal to 0, 1, 2, 3, 4, as I've mentioned earlier, have the terms as SPDF, usually written in capital block letters. By spin-orbit interaction, each energy level of a given value of L is splitted into two subshells. So if we have J is equal to L plus S, we have L plus half over here, and J is equal to L minus S, we have L minus half over here. And accordingly, we'll be having two subshells that are associated with them. Now, with the exception obviously for L is equal to 0. In that case, you'll have only a single value of J, and that is why there is no splitting involved. The splitting of the shell into two subshells that has been happening over here, no splitting involved in this case. Now the number of different possible orientations of L and S, and hence even the number of different possible values of J, is known as the multiplicity. And multiplicity is given by the factor 2s plus 1. So the multiplicity of one electron atom is equal to 2 times of in that case s is equal to 0, s is equal to half that we have been taking. So 2 times of half plus 1, so that gives us 2. It is added as a left superscript to the term symbol, just like this. So you have 2 of S, 2P, 2D, depending on the values of L, and so forth. So this is how these are known as doublet terms. Because they have two spectral, two lines, two subshells associated with them. In addition, the J value is added as the right subscript. So we have the term over here to be SPD, and we have the values corresponding for L to be equal to 0, 1, and 2. You have the values of J, for the J being fixed in this case, that is half, as I mentioned over here, and then we have the values of J to be 3 over 2 and half in this case, and finally 5 over 2 and 3 over 2 in this case. So the notation that we use in its entirety can be given as 2s half for the first one, of course. Then we have the next one to be equal to 2p3 over 2, 2p half, and then we have 2d 5 over 2, 2d 3 over 2. And if we even consider the principal quantum number, so in that case supposedly we have the case of 2, then we have 2p3 over 2. So this simply gives the information that n is equal to 2, L is equal to 1, S is equal to half, J is equal to 3 over 2. S will always have the value half, only the case of ms being equal to plus or minus half, that is plus or minus of S. But in this case J as we have seen J is equal to L plus minus of S. So that is why you are having two values of J, and hence the splitting factor. Now this was for single electron. Now in case of multi-electron atoms, what happens is that for multi-electron atoms, all the individual electrons, they couple to form a resultant angular momentum L, whose magnitude obviously is L times of L plus 1 h bar, that we have under root, and then we have all these spin quantum numbers. They add up vectorially to give a resultant spin quantum number, and finally these two they combine, they couple to give the corresponding total angular momentum. So this is how we calculate the case of the angular momentum as when we involve multi-electron atoms, or when we consider the multi-electron atoms. And in that case, what happens is that the term of the atom can now be in singlets or doublets or triplets and so forth. They are denoted in the same way that we denote the one electron atom as well. So in the subsequent portions that we are going to discuss, we will be discussing these factors in detail as well. So that's all from the case of the spin orbit interaction, as well as the terms and notations that are involved. And in the upcoming video in this series, we'll be discussing about the Stern-Gerlach experiment, which confirmed the case of the spinning of electron, although it was taken as it was a hypothesis that was postulated or taken up by the scientists Uhlenbeck and Smith, but still we obtained the proof of the spinning of electrons, the conformity to it, and that is what we are going to discuss in the upcoming video. Till then, thank you for watching.